Hi there, welcome to this video 6-3. We are going to talk about reverse chain rule and integration using this idea of U substitution. This is where the fun begins, alright? Are you ready? Strap yourselves in because this is about to get wild. Alright, our objective, integrate using U substitution, and we're going to start out with this idea of reverse chain rule, or undoing a chain rule. Now, the first two examples involve differentiation, where we have chain rule, and if I was to differentiate 1 plus 5x to the power of 4, well, I have to take the derivative of the outside, 4 times 1 plus 5x to the power of 3, but now I have to multiply times the derivative of the inside, times 5. There's the chain, or the hook-on factor. All right, example number 2, what's the derivative of sine of 1 plus 5x? So the derivative of sine is cosine of 1 plus 5x times the derivative of the inside, which is 5. Well, we're talking about integration. Integration is the opposite or the inverse of differentiation. So if I wanted to go ahead and integrate a function that has one function inside of another, so now I have the 1 plus 5x to the power of 3. Well, if I'm going to go ahead and undo differentiation, I have to account for that hook-on factor. And the derivative of this function, the derivative, if I called this u of this, the derivative of that is just 5 dx. Okay, so when I integrate, this and this are going to go ahead and go away. Okay, so now this gives me 1 plus 5x to the power of 4, and I'm going to divide by 4, and I have my constant. That's kind of the idea of what we're going to look at today. Same idea here, right? Didn't I just go ahead and take a derivative of sine of 1 plus 5x, and we had that hook-on factor? So I have to go ahead and undo that multiplication of that hook-on factor from this inside function. So that's going to go ahead and go away along with the dx. So when I integrate, integration of cosine is sine. So 1 plus 5x plus c. All right, let's go ahead and investigate this a little bit further and see how this applies to everything that we've been doing. All right, you must insert the chain rule factor, the derivative of the inside function, in examples 1 and 2. So when we integrate, we have to delete the derivative of the inside in examples 3 and 4. Now, each of the integration rules from the last couple of lessons can be adapted and applied to the chain rule form, which we have seen before when taking a derivative, and we can kind of investigate this here. And a basic example of this, the integral of e to the x is e to the x. Well, what if instead of x now, if I have a function there, some other type of function, we'll call it e to the u. Well, if I'm going to integrate that and there's a function there, I better have u prime there to undo, okay? And that's going to go ahead and get deleted. And obviously the integral of e to the u is just e to the u, which gives us this rule. So you can go ahead, pause the video, you can take a second and look at all these, but you'll notice if I'm integrating a function and I'm going to use a certain rule, and there's a function inside, like a function raised to a power, well, before I can use the power rule, I better have that u prime to delete or unhook, if you will, from my last example. Okay, so let's go ahead and look at some examples and see how this comes into play. All right, I want to integrate the 3x minus 1 to the power of 10 with respect to x. So what you should see here first is that 3x minus 1 is a function. If I wanted to go ahead and integrate u to the power of 10, hey, no problem here, right? That is just pure power rule. I can just add 1 to the power, divide by that new power. Well, I have that function, so I have to go ahead and I have to account for the derivative of that inside function. And the derivative, I'll call it du, the derivative of u, what I'm calling u, is just 3, right? Derivative of that is 3. And then I'll also add on the dx here, because the derivative of x is dx, okay? So notice, I don't really have a 3 here. I don't have that 3, which this would be my hook-on factor that's going to go ahead and go away when I integrate. So I can multiply in the 3, but I have to keep it balanced, because really I can only multiply something by 1. If I multiply something by 1, it remains unchanged. So if I'm going to multiply by 3, I also multiply by the reciprocal of this, and that keeps my equation balanced, right? I really only multiply by 1, so I didn't change it. Okay, so now that I added in the hook-on factor, now that I added it in, I can go ahead and rewrite this. So I have to bring down my 1/3, and this is u to the power of 10, and then here is my du, okay, the 3 dx. Okay, so when I integrate, that goes away, and we get 1/3, okay, u to the power of 11, and we're going to divide by 11. All right, but u is 3x minus 1. Now I'm going to plug that back in. 3x minus 1. Okay, so our answer here is 1/33 times 3x minus 1 to the power 11. And we have a plus c on the end. Don't forget that. Okay, so there's example 1. Let me go ahead and show you another example. Example number 6. Okay, and sometimes it requires you to be able to kind of see the connections. And one strategy you can do is look for the piece with the higher powers, because when I take a derivative, I know that those powers are going to be coming down. All right, so what if I have t cubed plus t squared? Well, the derivative of that, the hook-on factor of that, would be 3t squared plus 2t dt. And check it out. Don't I have my dt right there? Okay. And then don't I have 3t squared plus 2t right there? I do. So let me go ahead and just kind of restructure this. So I have t cubed plus t squared times 3t squared plus 2t dt. And then here is our hook-on factor, which when I integrate, that's going to go away. And essentially, I'm integrating this form, the integral of u du. Okay, and now how do I just integrate using the basic power rule? Well, power is going to raise by 1, so this becomes u squared divided by 2. But instead of u, again, and now I'm going to substitute back that t cubed plus t squared. Plus t squared. Okay? And there's our answer. All right, next example. Get rid of this. Next example. Oh, man, I have a lot going on. Whenever I have a function over another function, what I recommend doing is just going ahead and bringing it up. So I'm going to call this the integral of 4x cubed minus 5 to the power of negative 1/2, okay, times 6x squared dx. All right, whenever you encounter this situation, especially with a radical in the denominator, go ahead and say, hey, my denominator is going to be u. U is equal to 4x cubed minus 5, and then the derivative of that is 12x squared, and I'll add on a dx. Okay, well, I have 6x squared dx, but notice I'm down a multiplier of 2. I need to double that. Well, hey, no problem. I can multiply in a 2, so 2 times that. But when I multiply in a 2, you have to keep it balanced. So I'm going to multiply out front by 1/2. Okay, and let me go ahead and switch up my pen here. Okay, so now this is 1/2 times the integral of u to the power of negative 1/2. And then all of this, my hook-on factor here, that's going to go away. I'm just going to, for now, since I switched to u, I'll call that du. And now I'm just going to integrate. So this is equal to 1/2. U ends up getting raised by 1. So u to the power of 1/2 divided by 1/2 plus c. Okay, so I hope you see here that the 1/2s cancel out. and we end up just having u to the power of 1/2 plus c. And again, u was t cubed plus, is it? No, I'm thinking of the last problem. What am I thinking? 4x cubed minus 5. Okay, there you go. All right, let's see if you guys can go ahead and try one of these, if you can recognize the hook on factors and set this up. Here is your first example. Go ahead, pause the video, try integrating this one. All right, here is kind of the setup before I show you the answer. Hopefully you see you have an inside function there, 5t minus 3. Because something to the 8th power, integrating that would be no problem, right? U to the 8th becomes u to the 9th divided by 9. Well, I do have this inside function, so then du is going to be equal to 5 dt. Okay, if you haven't finished it, if you got stuck, try that, and go ahead and come back. All right, here is the solution. All right, so when you introduce that hook-on factor of 5, you also have to balance it with the 1/5, and then your power increases by 1 to 9. Divide by your new power, which is dividing by 9, or multiplying by 1/9, and you get your answer. Did you get it right? Good job, good job. Okay, next couple of examples. Number 8, man, I got something in my eye. Whew. Okay. Number 8 is kind of like a I mean, we can't do what we've been doing kind of situation. Why? Why, Schwarberg? Why can't we do it? Well, what if u is y cubed plus 1? The derivative of that would be 3y squared dy. And notice, in my function, I don't have any other y squared terms. I don't have it. I can't introduce variables. I can introduce multiples, but I can't introduce variables. So what we're going to go ahead and do, we're going to go a different route with this. We're just going to expand this integral to be y cubed plus 1 times y cubed plus 1 dy. And if I expand it out like this, I can now go ahead and multiply this out to give me y to the power of 6 plus 2y cubed plus 1 dy. And I can integrate that now just piece by piece. The integral of y to the power of 6 becomes y to the power of 7 divided by 7. Y to the power of 3 becomes y to the power of 4 divided by 4. And then the integral of 1 dy is just y. There it is. Not too complicated. So if you have a low level power, you can go ahead and expand it out. But I would look for connections if it got too much bigger. Okay, integral of sine of 4x dx. Well, hey, I'm going to say u is 4x. All right, there's a function inside of another function. So the hook-on factor of that would just be 4. So I have to account for a 4. All right, I'm going to multiply it in, but I'm also going to balance. Okay, so this becomes 1/4 times the integral of sine of u du, right? There's the hook-on factor that's going to go ahead and go away. And the derivative, or sorry, the integral of sine is just negative cosine. So 1/4 times negative cosine of u, which is 4x, plus c. So I would rewrite it like this. All right, there is example number 9. All right, and one that is similar here, we have the integral of 3 theta cosine of theta squared d theta. Whenever you have a trig function, this kind of bugs me. I wish problems would just automatically put parentheses here. That's your argument, theta squared, okay? So here, again, this is the highest power. And I'm going to let that be my u function, because when I take a derivative of that, the power is only going to go down. So I have 2 theta times the derivative of theta. So notice with theta, I already have another theta here. I have a d theta, but I don't have a 2. So, okay, well, I'm going to multiply in a 2. And I'm going to balance it with a 1/2. Schwarberg, what about the 3? Well, let me go ahead and just pull out the 3. 3 over 2, right? Integral of cosine of u times du, right? Here's your hook-on factor along with this. Okay? All right, well, now if I integrate, so 3/2, the integral of cosine is sine, and we are done. Not difficult, right? You just got to find the connections, find the patterns, and you guys are very good at that. All right. Here is a practice problem. Okay, all right, try to identify the main function and then the derivative of it that you can use to get rid of that hook-on factor. All right, hopefully you tried this one. This one requires u to be the function in the denominator, 2x squared minus 4x, and the derivative of that would be 4x minus 4. And I know you're like, Schwarberg, I don't have 4x minus 4. What if you factored out a 4? Do you have an x minus 1? If you got stuck, go ahead, try this. Pause me one more time before I show you the answer. Okay, here is the answer. So if we introduce that 4, the hook-on factor of 4, you have to balance it with a 1/4 out front. Obviously, we have a power of -5 because the function was in the denominator. So using negative exponent rule, we bring it up. Okay, we'll add 1 to the power, giving us -4, and then we'll divide by that new power. And then there is our answer. Not too hard, yeah? All right, last example I have for you. Here we have the integral of sine squared x cosine x dx. Again, this is, when it's in this notation, this is sine of x squared times cosine of x dx. Now, the great thing about trig functions like this is you can often identify one function as the derivative of the other, especially with sine and cosine. So if I let u be the sine of x, the derivative of this is cosine of x. There we go. Hey, check it out. There's our hook-on factor. I didn't even have to multiply anything in. All right. So what is the integral? And the rule I'm using, right, is just power rule. U squared, right? That's sine here. U squared du. Okay, this becomes sine of x to the power of 3 divided by 3 plus c. Okay, and you might even see this answer written like this: 1/3 of sine cubed x plus c. Both of these are equivalent formats. Okay. All right, I have one more practice problem for you here. Try this one, and then I'll go over the answer here in a second. Okay, for this example, your u function is cotangent of t, because the derivative of cotangent is negative cosecant squared t dt. All right, if that helps you out, pause me, complete it, and I'll go over the solution. All right, here is the answer. So cosecant squared of t, that's your hook-on factor, and obviously, like we said, we had a negative here, and since we didn't have one, we had to introduce it and then balance it. That's where the other negative comes from. Using the negative exponent rule, bringing up the cotangent to the power of -4, that gives us, when we add 1, -3, divide by -3, and you could see it in this format. Okay, I'm going to go ahead and split the video before we get to our u substitution. I know this is a lot. Pause the video a lot. Practice this. And I hope you learned something. Okay, give me a thumbs up. Subscribe. I'll catch you in the next video where we talk about u substitution.